Today we're going to talk about what exactly PCS statistics mean on a given 100 gig link. So most of the times on every 100 gig link, for example, you will see these counters being displayed with majority of the vendors. In this example, I have a Juniper interface which is 100 gig capable. And on this interface, when I do show interface, as you can see on the screen, it displays PCS statistics with bit errored seconds count and block errored counts. So what this really means is what we're going to talk here in this video. It really has some significant importance because if you see a lot of bit and block errors, it can indicate that there is a problem in the physical layer, and higher rate of bit errors and block errors can also result in links flapping, like you can have a sudden micro flap kind of scenarios. The one more key point to note is that whenever you see these errors, it does not really always mean that your data packet is having an impact. So what I mean by data packet is your actual content. If that is getting corrupted, you need to look at something called as frame check sequence counters. So first let's walk to what this PCS statistics is and how this PCS logic works. So on the screen here, I have the format of PCS. In PCS, there are two formats. There is a control format and a data format. Now for data block, whenever data is being sent, the number should always start with 0, 1. For control block, the number will start with 1, 0. For every control block, there is something called as a block type. I will explain what this block type means, but what is more important to take away is control block and data blocks are the key parts of a PCS technology before it transfers data. So the start will always have a control block, the end will also have a control block, and in between them will be data blocks. So as soon as you see 1, 0, it is a control block. As soon as you see 0, 1, it is a data block. That is something we need to remember. Now, within the control block, there are different types of block types. You see the block type I was talking about? So all these are control blocks because they all start with a 10. So if it is an idle block, the block type will be 0x1e. If it is a start of frame, because we know that before the data starts transferring in the PCS layer, which is a part of the physical layer for 100 gig, first you will always have a control block, then the block type will be given, and then the data will be added. Likewise, at the termination point or finishing of data transfer, again you will have a control block, then the block type telling that it is finished transferring data, and whatever data is left will be added on the D block. The D here stands for data blocks or the packet payload that we are carrying. So for start of a frame, right, the control block and the block type will be 78. That indicates that this is the start of frame. For a terminate block, so where I have finished transferring data after this control block, I will put a block type as FF. I've given explanation for that as well. A hex value 78 indicates start of frame, with each DN where n is 0 to 7 is basically indicating data bytes. A maximum of 7 data bytes or 56 bits can be sent across each control block. One important thing to note is the total length here for a control block or a data block is 66 bits. So there is a 8 bits for data and another 8 bytes for data. So which is 8 times 8 is 64 bits, and another 2 bits for your control, where you say 1, 0 for control or 0, 1 for data. So it's totally a 66 bits information that is carried. Now I'll go further to explain the data block. So data block, as we know, will always start with a 0, 1 followed by data, where n represents the data block, so 0 to 7. Now a maximum of 8 bytes of data, which is 64 bits, can be sent across each data block, excluding the sync bits, which is the 2 bits I was talking about. The sync bits are the 0, 1. So that is what, if you add 64 and 2, that is the 66 bits we talk about. So whenever we talk about PCS, we either talk about it as a 66 bits or a 64/66 bits, because 64 is for data and the 2 bits is for the sync. Now there is a table here that explains the different block types you can have. So you can see that the sync bit 0, 1 is obviously data followed by all the data. 10 is the different flavors of control types for control PCS blocks. And you can see the block types have different meanings here, different numbers. So 78 is start of frame. For example, 87, if I look at the block type 87, that is pretty much saying that it is finished transferring the frames and there's nothing to send, with C, which indicates an idle. When you have C in these data blocks, it indicates there's nothing much to send but just idle blocks. Likewise, when the block type was 0x1E, it says that it's only sending only control or idle bytes, idle bytes. So there is a significance. When you see 78, I know it's a start of frame. For example, if I see 87, I know it's completely, idle along with end of frame. And if you, let's say, have a scenario where you still have to send 1 byte of data, you can put a block type of 99 followed by that 1 byte of data and then all idle blocks. So I have further example to demonstrate this. So example, if you want to send a data from one Juniper box to another or any other vendor that is pretty much using the same concept. So how does it work? Let's pick an example where I need to send a 15 byte traffic from left to right. At L1 after PCS processing, right? So what really happens? First, we know before start to send the data, we have to have a control block, which is the sync bit with the number 10, then followed by a block type, which is start of frame indication, which is 78, followed by data. So because one block type is taking 1 byte, I can only send 7 bytes of data, which is what is left. That is what D1 to D7 is. You can see I'm not using D0. Then followed by that is the data block, which is its value of 01. The control sync is 01. As soon as you see 01, you know it is a data block. And then I am putting the remaining 8 bytes. So 8 plus 7 is the 15 bytes that I've already finished sending. So now that within my data block I have finished sending the 15 bytes after D7, I have to finish off this sequence by using another control block, which is a value of 10. And here the block type I put as 87 because there is no more data to send. So I fill up all these data blocks with C1, which is idle frames. So that's the logic in which it is sending it. Now you may think, is it really significant to know this level of data? Of course, it is important because ultimately, as these values are being sent on wire, the ASIC, when it is doing the PCS calibration, it's looking for these control blocks and these data block synchronized bits. As soon as these bits start being in the wrong place, that is when we start recording bit and block errors. So when do we record bit errors? When do we record block errors? Because you have two columns here. There's a bit error block and a block error block. So I need to know at which problematic scenario these counters start working. So just taking one more example, if you have to send only 8 bytes of data, you can see how this starts off with. Again, start off with the control block of 10 with the start of frame with the value of 78, followed by data, that is 1 to 7. Now here you can see I have one more data left to be sent, which is why I finish off with the another control block of 10, the bit sync bit, with the block type of 99. Because previously, you see I was sending a block type of 87 because I had no data to send, as the previous data block already finished it off and I just filled the data block with idle blocks. Whereas here I have one data to be sent, which is why the block type changes from 87 to 99, and that is what is explained here as well. So if you have one data to be sent, you have a block type of 99 followed by one data with idle. If you have two data to send or 2 bytes left to send, your block type will be 0xAA followed by the 2 bytes and then idle block. So there are different ways in which you can send. Now with that logic, you can see block type is 99 followed by that 1 byte of data followed by idle blocks. Now same story, if you pick a bigger byte like a 640 byte packet, so how many control blocks are you going to have? How many data blocks are you going to have? Starts off with one control block, which is 10, followed by the sync bit, which is telling the start of frame 78 plus 7 data bytes. Then for 79 times I will have data block that starts with a value of 01, because each of these 79 times of 01 will have 8 bytes of data. Then finally I will finish it off with another one count of control block which starts with 10, then 1 data byte with end of frame. So I'm just calculating how many times I'm repeating it, and you can see this is how I reach 640 bytes of my data with 79 time counts of data block which starts with the sync bit of 01. So data block, as you know, is this one here, 01. So 79 times of 01 with followed by 8 bytes of data. Likewise, two control blocks, one with start of frame with 7 data bytes and one with a block type of 99 with 1 data byte. So now moving to the interesting part, as you now know the logic in how these data blocks and control blocks are used, now let's look at how the routers or devices record bit and block errors. So we know that 0, 1 and 1, 0 are important. Now if those bits are flipped, that is actually the bit error, that is the BER error. So whenever those sync bits are not in the correct order, we end up recording as bit errors. Now that only focuses the 2 bits, out of the 66 bits, because we clearly spoke about the total length being 66, because 64 for the 8 bytes of data, and then you have the 2 sync bits. Now the bit error BER is only tracking these 2 sync bits, 10 or 01. In this example, you can take it as 10 or 01. That's what it's tracking, and it will record an error. Now when these bit error counts are higher, right, for like 125 microseconds, if I have X number of errors, that's when link goes down. So that's an indication that the PCS is not able to maintain the synchronization in the control block. So when there is a higher rate of errors, it's called high bit error rate, and the link goes down. And you will naturally have local fault, remote fault accordingly to indicate the direction of fault. Now, I have already posted videos on what is local fault and remote fault. You can refer to that video on the channel. So one important point to note is, if only one bit within the sync header, when I say sync header, the sync headers are these ones here. Again, just to iterate, whether it is this one, 10 or 01. So if only one bit of the sync header is incorrect, so for example, instead of being 10, it is 00 or 11, then it is classified as bit and block error. So when you see both bit and block errors increasing on your counters, here bit errors and block errors, you know that there is a very high possibility that there is a single bit flip between the control block and the data block. So that is possible. When both the 2 bits of sync header is incorrect, that is, instead of being a 10, it is 00 or things like that, then it is treated as a block error only. There is no bit error. So if you notice sometimes that only blocks errors are increasing, you know that both the sync bits are in the wrong place. If you notice that bit error and block errors are both increasing together, then you know only one bit within the control and data block is changed or incorrect. So it just gives you an idea of the level of problem you may have in the physical layer. So when the 2 sync headers are correct, imagine that if the 10 and 01 are in the right place, like as we spoke here, they're all in the right place. But if the block type is wrong, it doesn't give you the correct representation. So what does it be treated as? So when the 2 sync header bits are correct and the block type is incorrect, then it is treated as a block error. So only block errors will happen. However, one important point here is, just because you have these sync bits in the wrong place, does it mean my data is impacted? No. So if you just see that the PCS bit and block errors are happening, there is no need to panic and think that my data is also corrupted. That is very important to remember. PCS statistics is only focusing on the sync bits and the block type. The moment you have a very high burst of errors on the sync bit and the block type, there is a very high possibility if you reach the threshold for errors within a set of seconds, the link will flap. But that does not mean that your data is corrupted, because when your data is corrupted, you should normally look at a different counter, which is what I'm going to explain. So when your data is corrupted, a bit error in the data type is not detected at the PCS, will be detected at the frame check sequence counter. So you need to look at the frame check sequence counter on a Juniper. Where it is, I will explain. Other vendors may record it as CRC errors. So that is the key differentiation. So if you really want to check whether my data is impacted because of bit and block errors, you need to check if your CRC or frame check sequence counters are increasing. As long as you do not have an FCS counter or CRC is increasing, that only indicates that your data is fine, but only the control bits and data bits blocks, the sync bits are in an incorrect location. But it still means that there is a possibility that the link may flap. However, as long as it continues to trickle with these errors, but you don't see CRC errors and FCS errors, you can be assured that your data is not corrupted. That's one important takeaway from these points of discussion. Now, as you can see here, I will show you where exactly you need to look for the CRC. Now, PCS does not drop the block just because it has a bit and a block error. However, it keeps track on the number of bit and block errors for link threshold for bit errors. So that is another indication. Just because we see PCS bit and block error, it really does not mean that we are dropping the packet. But you need to keep a close tab on the frequency in which they are increasing. At least it gives you an indication that if the errors start off rapidly going up, you know that there is an inevitable link flap that may happen any moment. And then in combination with that, you look at your FCS counters or CRC counters, and that is here. For example, in a Juniper, you have something called as input errors. When you do show interface extensive, under input errors, you should look for something called as framing errors, which is frame check sequence or CRC. The moment you start seeing that, that is where the real problem is, where your customer data can get impacted. So as you can see, it's also mentioned here. Although PCS counters are good for monitoring link quality, interpretation is needed to understand if there is an underlying problem. So the best thing to do is look at the higher level of counters, which gives you more valuable data on the user traffic. So FCS field is the CRC field calculated. So you need to look at the input error counter, look for any framing errors. The moment you start seeing this, you know for sure that your customer data is also now starting to get impacted. And in terms of troubleshooting, so once you know that you have bit and block errors, you also have framing errors, or you may not have framing errors, you just have bit and block errors. How do you approach these kind of problems? The best is to look at the fiber. Usually dirty fibers can do that, bad fibers can do that, optics can do it. If you have a faulty optic, in this case I'm just referencing a CFP, which is the first generation 100 gig optics. Now you have different flavors of QSFP28 or QSFP28 double density optics. So those are things that you can refer to. Sometimes even the optics could be good, the PIC module or even the line card could be faulty. So sequence of troubleshooting is to start from the physical layer, start off with the cleaning of the fibers with the fiber scope. If that doesn't help, try to change the fiber cable. Again, if that doesn't help, then follow to the next process of swapping out an optic. And if you know that the new optic is also reporting the same problem at both ends, then obviously you can start isolating with one direction by changing the PIC or the line card. In case of a Juniper, in case of a Cisco or other vendor, you look at those corresponding objects. So hope you find this useful. Bye for now.